Every video here exists because people chose to support it. If you would like to be part of that, the link is in the description. There is a hum, not from the science itself, from the laptop fan running too warm on a desk that probably needed clearing 2 weeks ago. That kind of background noise. The kind you stop hearing. And the reason I mention it is that the thing we're about to sit with tonight has a very similar quality. It has been running in the background of cosmology for years, just below the level where most people pay attention. And the scientists who do pay attention have started to find it not alarming exactly, more like persistent, a hum that won't stop when you expect it to. The number is the Hubble constant. Or rather, the problem is that the Hubble constant is two different numbers, depending on how you measure it, and no one can figure out why. Let's stay with the basics for a moment, because they matter, and because they're actually not complicated. The Hubble constant, usually written as h0, is just a way of describing how fast the universe is expanding right now. For every megaparsec of distance between 2 points in space, a megaparsec being about 3.26 million light-years, which is already a distance that stops meaning anything the moment you try to picture it, those 2 points are moving apart at a rate expressed in kilometers per second. That's all it is, a speed per unit of distance. Edwin Hubble measured it badly in 1929. We have been refining it ever since. There are two main ways to do the measuring. The first is called the distance ladder. You look at objects relatively nearby to feed variable stars which pulse at rates that reveal their true brightness, and type 1 are supernovae, which explode with a consistency that makes them useful as cosmic measuring sticks. You figure out how fast those objects are receding. You build up a chain of distances, each link calibrated against the last, stretching outward from our own galaxy until you have covered enough ground to get a reliable speed. When you do this, and teams have been doing this carefully, with Hubble Space Telescope data, with JWST data, with cross-checks and rechecks, you get a number around 73 kilometers per second per megaparsec, give or take a little. The error bars have gotten very small. The second way is entirely different. You go back almost to the beginning. The cosmic microwave background is the afterglow of the early universe, light that's been travelling since roughly 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and photons to finally move freely. The temperature fluctuations in that background light encode, with extraordinary precision, the state of the early universe. And from that state, using the standard model of cosmology, you can calculate what h0 should be today. The Planck satellite measured those fluctuations with enormous care. WMAP did it too. The answer is consistently around 67 kilometers per second per megaparsec. 67 and 73. In ordinary life, the difference between 67 and 73 of anything is almost nothing. 6 kilometers per hour over a long drive, 6 degrees of temperature. You wouldn't think about it. But cosmology is not ordinary life, and here those 6 units are. Well, they represent completely different stories about what the universe has been doing and what it is about to do. The teams who get 73 are not making mistakes. The error bars on the SH0ES project, which uses Cepheids and supernovae, have been reduced to less than 2%. Adam Rees, who led that work, is the same person who won the Nobel Prize for discovering that the universe's expansion is accelerating. He's not new to this. He knows what careful looks like. The teams who get 67 are also not making mistakes. The Planck satellite's measurement of the cosmic microwave background is one of the most precise measurements in the history of observational science. The Atacama Cosmology Telescope confirmed it. DESY's baryon acoustic oscillation surveys, which use the clustering of galaxies as a kind of frozen record of ancient sound waves, also land near a 67, several completely independent methods, using completely different physics, arriving at almost the same place. So here is the question that doesn't have a comfortable answer. How can both be right? For a while, the hope was that one side was slightly wrong, systematic errors, unaccounted for dust, something in the calibration of the distance ladder that would, once found, bring the two numbers into agreement. JWST was supposed to help. When it turned its eyes toward the Cepheid variables that anchor the distance ladder, what it found was not a correction. The Cepheids held, the local rate held, the number stayed near 73, the tension, as it's called, deepened rather than dissolved. The tension is now at something like 5 sigma. In physics, sigma is a way of measuring how confident you are that a result is real rather than accidental. 1 sigma is a shrug. 3 sigma makes people interested. 5 sigma is what physicists require before they will call something a discovery. The Hubble tension has reached that threshold, not as a discovery of something new, but as a confirmed, statistically robust disagreement between two ways of understanding the same universe. What that means, if it holds, is that something is missing from the model, not a small calibration fix, something structural. One possibility, and I want to be careful here, because this is still very much a live argument rather than a settled conclusion, is that the universe contains some form of energy that was active in the early cosmos but has since changed or faded. Early dark energy, some researchers call it. A temporary boost in the expansion rate around the time when the microwave background was forming, which would shift the early universe predictions upward toward the late universe measurements. It's a possible explanation. It's also, as of now, unconfirmed. Another possibility is something simpler and stranger. That dark energy is not a constant. That the energy driving the expansion of the universe is not a fixed property of empty space, but something that evolves, something that has changed over the lifetime of the cosmos and may still be changing. If that's true, the early and late universe would naturally return different values for H0 because H0 would not in fact be constant. The measurement gap would not be a flaw, it would be a window. This is not a fringe idea. DESI's most recent data, released through 2024 and into 2025, analysed the distribution of galaxies across enormous volumes of space and found hints, statistically real hints, that dark energy may have behaved differently in the early universe than it does now. The standard model, lambda CDM, treats dark energy as an unchanging cosmological constant. The DESI data, when fit to models that allow dark energy to vary, produces better fits. Not proof, but not nothing. And here is where something shifts a little in how you have to hold this topic. Because if dark energy evolves, then the question of what it's doing right now, tonight, as this particular corner of space-time expands at whatever rate it's actually expanding, is an open one. It might be weakening. It might be holding steady. Or it might be the thing that some cosmologists have been reluctant to say directly for years, strengthening, growing denser as the universe expands rather than diluting, feeding on its own momentum. That last possibility has a name. It's called phantom energy, and it leads, in the mathematics, to a specific kind of end, not a slow fade, not a gradual cooling, but a shredding, a point at which the expansion accelerates beyond any physical constraint, and everything that exists is pulled apart by the stretching of space itself. The Big Rip. I want to be clear that we are not there yet, not in the evidence, not in the consensus. The Hubble tension does not prove phantom energy. The DESI anomalies do not confirm that dark energy is growing. What they do is keep a door open that most physicists were hoping to close. The possibility is still inside the data, sitting there, unresolved like a number that won't agree with itself, no matter how carefully you check the arithmetic. There is a kind of pressure that comes from sitting with an open question, not an uncomfortable pressure, more like the feeling of holding something in your hand and not yet knowing what it is. The weight is real, the thing is real, you just don't know its name yet. The two numbers, 67 and 73, are still both there, still both measured, still both defensible by careful, serious people using rigorous methods. And in the space between them, something about the universe's past, its present state, and possibly its end remains unresolved. Not because we haven't looked hard enough, because whatever is hiding there is patient. The numbers won't agree. And that, it turns out, might be the most important thing they've told us. There is something almost counterintuitive about what JWST was originally supposed to do for the Hubble tension. The expectation, and it was a reasonable one, shared by a lot of careful people, was that a better telescope would produce cleaner data, and cleaner data would produce a cleaner answer. The logic was tidy, too tidy maybe. JWST launched in December 2021. It spent months unfolding itself in the cold of space, mirror by mirror, like something that had been waiting a long time to open. By mid-2022, it was operational, already sending back images that made people stop whatever they were doing to look at them properly. And among the first serious scientific tasks it was handed was this one. Look at the Cepheid variable stars that anchor the local measurement of the Hubble constant and tell us if the older measurements were right. Cepheid variables are stars that breathe. That is not exactly the technical description, but it is not wrong either. They expand and contract over regular periods, days to months, and the rhythm of that pulsation is directly tied to their true luminosity. Measure the period, know the brightness. Know the brightness, measure the distance. It is one of the oldest and most reliable tools in observational astronomy, going back to Henrietta Swan Leavitt in 1908, who noticed the pattern in a set of stars in the Magellanic Clouds while working as a human computer at Harvard, doing calculations for wages that were, by any measure, embarrassing. The tool she gave us outlasted every injustice of the context in which she built it. What astronomers worried about going into the JWST era was that the Hubble Space Telescope, which had been the primary instrument for Cepheid measurements, might have been suffering from crowding. In dense stellar fields, nearby stars can bleed their light into the measured brightness of a Coherent, making it appear slightly brighter than it is, which makes it appear slightly closer, which nudges the Hubble constant upward. The concern was specific and testable. JWST's sharper resolution would separate the stars more cleanly, and the local H0 value would come down, smoothing the tension with the early universe measurement. It didn't. When the JWST Cepheid results came through, from Adam Ries's team, the same group responsible for the original Nobel-winning supernova work, the contamination was real but small. Correcting for it did bring the local measurement down slightly, but not enough, not nearly enough. The number landed, after all the correction, still comfortably above 70. The Planck value of 67 remained on the other side of a gap that had not meaningfully narrowed. This is the part that is hard to absorb without a small quiet feeling of something like, I am not sure what to call it. Not disappointment, more like the specific experience of rereading a sentence in a letter you've received and realizing that what you thought it meant the first time is not what it means. The words are the same, your reading of them is more careful now. The message is still unclear. JWST was supposed to resolve. Instead, it confirmed. And those are very different outcomes. The confirmation matters because it closes a specific exit route. Before JWST, one of the main hopes for explaining the Hubble tension was instrumental. Perhaps the older telescope's limitations had introduced a systematic error large enough to account for the discrepancy. That hope is no longer credible. The distance ladder, measured with the best available instrument, still returns a local expansion rate that disagrees with what the early universe predicts. Whatever is causing that gap, it is not the telescope. Somewhere around this point in thinking through what JWST found, another data source enters the picture, not loudly and without any particular fanfare. The Euclid Space Telescope, operated by the European Space Agency, began returning early results in 2024. It was designed for a different purpose than JWST, not to look at individual stars in sharp detail, but to map the large-scale structure of the universe across enormous volumes of space. Its primary science goal is weak gravitational lensing, the way the invisible mass of dark matter bends light from distant galaxies, creating subtle distortions in their apparent shapes that, aggregated across millions of sources, trace the web of structure that dark matter weaves through space. Euclid is not primarily a Hubble constant mission, but the data it produces touches the same questions from a different angle, the way you can sometimes understand a room better by standing in the doorway than by standing at the center. Its early weak lensing results confirmed the large-scale structure of the universe with impressive precision, and in doing so they added another voice to a conversation that was already crowded, not resolving the Hubble tension, but making it harder to attribute to any single measurement artifact. If JWST confirmed the local rate from one direction, and Euclid confirmed the clustering behavior of matter from another, then the picture being assembled is one of genuine multi-method, multi-instrument disagreement. Not noise, not carelessness, something structural in the model that doesn't quite fit. There is a detail from the Euclid data worth sitting with. The amplitude of matter clustering, a quantity called S8, which describes how clumpy the universe is on large scales, came in slightly low compared to Planck predictions. Not dramatically, not enough to declare a new crisis, but it is the same direction of discrepancy that other weak lensing surveys, like the Kilo Degree Survey and the Dark Energy Survey, had already hinted at. The early universe, as described by Planck, predicts a slightly clumpier cosmos than the one we actually observe when we look at large-scale structure today. Euclid, with its far larger survey area and cleaner measurements, confirmed that mild shortfall. What this might mean is genuinely unclear. It could mean that dark matter behaves slightly differently than the standard model assumes, that it has some small interaction or property that smooths structure on large scales. It could mean that dark energy is not constant, and that its evolution over cosmic time has subtly altered how structure grew. Or it could mean something that no one has clearly articulated yet, because the combination of H0 tension and S8 tension doesn't map neatly onto any single existing explanation. The two discrepancies live in different parts of the physics. Getting a model to resolve both simultaneously has turned out to be, well, stubborn is probably the right word. The difficulty is that the standard model of cosmology, lambda c dm, is, by almost every other measure, extraordinarily successful. It predicts the large-scale structure of the universe. It correctly describes the acoustic peaks in the cosmic microwave background. It accounts for the abundances of light elements produced in the first minutes after the Big Bang. It is not a bad model looking for excuses. It is an excellent model that happens to return two values for the expansion rate that don't match, and a matter clustering amplitude that sits just slightly below expectation, and a growing collection of data from instruments operating at the edge of what human engineering has ever achieved, all of which suggests that something somewhere in the model is a little wrong. A little wrong is not nothing. In physics, a little wrong in the right place can mean completely wrong in the long run. I keep coming back to what evolving dark energy would actually require of the model, not just as a mathematical addition but as a conceptual one. Lambda CDM treats dark energy as the cosmological constant, a fixed energy density belonging to empty space, the same everywhere and at all times. Adding time variation to that requires introducing something new, a field or a mechanism or a behavior that the current framework has no natural place for. The DESI baryon acoustic oscillation results, which use galaxy clustering across different cosmic epochs to measure the expansion history, found hints, not proof, but statistically interesting hints, that the equation of state of dark energy may have been different in the earlier universe than it is now. The data preferred a dark energy that wasn't quite constant. That had moved. If it moved once, it could move again. This is not something JWST measured directly. It is not something Euclid confirmed cleanly. It is an inference, sitting downstream from multiple separate datasets, arrived at by asking what kind of dark energy would produce the expansion history those datasets collectively describe. And the answer, in at least some analyses, is not a constant one. The letter metaphor is wearing thin by now, and I'm not going to push it further. But there is still something in this situation. The accumulated weight of instruments reporting in from different distances, different epochs, different physical methods, all contributing to a picture that is more detailed than the one we had 10 years ago, and still, somehow, less resolved. That feels like correspondence with something that won't quite answer you directly. You get more letters, the handwriting gets clearer, the meaning stays just outside of clean paraphrase. What JWST found confirmed that the local universe is expanding at a rate that the early universe physics cannot straightforwardly explain. What Euclid found confirmed that matter in the late universe is slightly less clump than it should be, by the same early universe predictions. 2 telescopes, 2 different measurements, the same faint, persistent indication that something in the cosmological standard model is not exactly where we put it. Dark energy is the most likely place to look, not because it's the obvious culprit, it isn't, but because it is the part of the model we understand least, the part with the most room to hide a quiet mismatch between what we assumed and what is actually there. If it has been changing, slowly, over billions of years, in ways too gradual to notice without exactly these kinds of careful, cross-method, multi-instrument surveys, then the measurement gap might not be a gap at all. It might be a record. The universe keeping its own account of what dark energy has been doing all this time, written in the difference between 2 numbers that won't agree, 67 and 73 still there, and now joined by a third quiet signal from Euclid, a universe that clusters just slightly less than it should. The next question is what kind of dark energy produces this pattern? Whether it is holding steady weakening or, and this is where the mathematics becomes considerably less comfortable, accelerating. The name stuck because it was convenient. Hubble constant, a constant, something fixed and retrievable, the same regardless of when you measure it or where you stand in the universe. Edwin Hubble measured it in 1929 as somewhere around 500 kilometers per second per megaparsec, a number so far off from what we know now that it implied a universe younger than the oldest stars, which was awkward. Even at the time, the number changed. The name didn't. For most of the 20th century, the working assumption was that H0 was simply waiting to be measured correctly. The variation between estimates was treated as measurement error, instrument limitation, calibration disagreement. Get a better telescope, control the systematics, and eventually the number will converge on whatever it actually is. That assumption was reasonable. It was also, it turns out, doing a lot of quiet work that only becomes visible once the assumption starts to wobble. In cosmology, H0 is defined as the expansion rate of the universe at the present moment. That is the definition, present moment. But the universe has a history spanning roughly 13.8 billion years, and the expansion rate has not been the same throughout that history. In its earliest moments, the universe was decelerating. Matter and radiation were dense enough that gravity dominated, slowing the expansion down. Then somewhere around 5 to 9 billion years ago, something shifted. The expansion began to accelerate. Dark energy, or whatever it is that drives the acceleration, overtook the gravitational drag of matter, and the universe began moving outward faster with each passing era. So the expansion rate is not, and has never been, a static quantity. It changes over time. H0 is specifically the value of that changing rate right now, a snapshot, not a law. And this is where the assumption gets complicated. Because if you measure the snapshot directly, looking at nearby objects, building the distance ladder, watching stars pulsate and supernovae explode, you get one value. If you infer what the snapshot should be by modelling the universe's entire history forward from the early universe, using the microwave background, using baryon acoustic oscillations baked into the distribution of galaxies, you get another. And those two values don't agree. The question nobody has fully settled is whether this discrepancy is a measurement problem or a model problem. A measurement problem would mean one side is making an error. A model problem would mean the framework we use to translate early universe observations into a present-day expansion rate is missing something. What it would mean for the framework to be missing something is worth thinking through slowly. Lambda CDM, the standard model of cosmology, treats dark energy as a cosmological constant. Lambda, a fixed energy density belonging to empty space, unchanging across time and uniform across the universe. When you use Planck's microwave background data to infer H0, you are not just reading a number from the data, you are running the data through lambda CDM, using the model to translate an early universe measurement into a present-day prediction. The model carries lambda inside it. Lambda is constant. If lambda is not constant, if dark energy has evolved, was stronger or weaker in the early universe, has shifted since, then every H0 value inferred through the model is carrying a hidden error. Not from bad data, from a quietly wrong assumption embedded in the translation. This is not a new concern. Cosmologists have been exploring dark energy models with varying equations of state for years. Quintessence, early dark energy, interacting dark energy. There is no shortage of theoretical frameworks that allow dark energy to change over time. What has changed recently is that some of the observational data is starting to prefer these models over the constant one. Not overwhelmingly, not decisively, but with enough statistical weight that the preference is difficult to dismiss as noise. This is baryon acoustic oscillation analysis, released through 2024 and 2025, measured the clustering of galaxies at multiple cosmic epochs. The pattern of that clustering encodes the expansion history. The BAO scale acts like a ruler fixed by early universe physics, that can be measured at different distances and different times to trace how fast the universe was expanding at each point in its past. When DESI fit that expansion history to a model where dark energy's equation of state was allowed to vary, parameterized as W0, the present value, and WA, the rate of change, the fit was better than lambda CDM, meaningfully better. Better fit does not mean proof. This needs to be said plainly. A model with more parameters will almost always fit data better because it has more freedom. The question is whether the improvement in fit is large enough to justify the additional complexity, and whether the preferred parameter values make physical sense. In the DZ analysis, the preferred values suggested dark energy that was phantom-like in the recent past, meaning its equation of state dipped below -1, which implies energy density increasing with expansion, but less so at earlier times. That is an unusual trajectory, physically unusual, the kind of behaviour that standard scalar field models, quintessence, can't easily reproduce without additional assumptions. So the data prefers something, but that something doesn't cleanly map onto any existing well-motivated theory, which is, and I am not sure if this is reassuring or not, a fairly common place to be in physics when something new is starting to show up. What does it mean for H0 to not be a constant? Technically, H0 will always be defined as the present-day expansion rate. In that sense, it is always a constant, a single number, a snapshot. But if dark energy evolves, then the expansion history connecting the early universe to that snapshot is different from what lambda CDM computes. The inferred H0 from early universe data would shift, possibly towards 73, possibly to something else entirely. The gap might close, or it might close and reopen somewhere else in the model, because the same dark energy evolution that shifts H0 would also change the predicted clustering of matter, touching the S8 tension, touching structure formation, touching the age of the universe and the distribution of its oldest stars. The assumptions are not independent. Pull one and the others move. This is what makes evolving dark energy simultaneously appealing and uncomfortable as a solution. It addresses something real. It opens something larger. The Hubble constant is still being measured. New results arrive with some regularity. Gravitational wave standard sirens, surface brightness fluctuations, water mazes in distant galaxies, time delay cosmography from gravitationally lensed quasars. Each method is independent. Each has its own systematics. And the pattern, looked at across all of them, is a faint, persistent tendency for late universe methods to land higher than early universe methods. Not always, not without exceptions, but often enough that the split is looking less like scatter and more like structure. A number that has structure in how it disagrees with itself is not behaving like a constant. It may never have been one. The name was always just a convenience, a label applied early, before we had the tools to see what the thing was actually doing. Now the tools are sharper. The measurements are cleaner. And the thing they are pointing at is not a fixed value waiting to be recovered. It is something that has moved in some direction over the history of the universe. Whether it is still moving is what comes next. Science has a particular way of handling embarrassment. It files it, labels the folder systematic uncertainty or measurement artifact, or requires further study, slides it into a cabinet and moves on. This is not dishonesty. It is a kind of operational patience, the understanding that not every anomaly survives contact with better data, and that spending too much energy on a result that might dissolve in the next round of measurements is a poor use of limited resources. The filing cabinet is a reasonable place. Most things that go in it eventually turn out to belong there. The Hubble tension has been sitting in that cabinet since roughly 2016, and what has happened since is that instead of fading, it has gotten louder. The folder keeps getting thicker. By the time the discrepancy between local and early universe measurements of H0 reached 5 sigma, which it has, confirmed across multiple independent methods and multiple independent teams, it had stopped being the kind of thing you could file. 5 sigma is the threshold physicists set for discovery, not because 5 is a magical number, but because the probability of a genuine 5 sigma result being statistical noise is less than 1 in 3.5 million. You do not accidentally stumble into that territory. Something is producing the signal. What that something is remains, as of now, genuinely open. The shift in how cosmologists are relating to the tension is subtle but real, and it happened gradually over the last few years. Early on, say 2018, 2019, the dominant posture was corrective. The assumption was that one side was making a mistake. Not a careless mistake, not a dishonest one, but a systematic error of the kind that even excellent science produces. An unaccounted for bias in calibration, a subtle contamination in the stellar photometry, a theoretical assumption baked into the data analysis that was slightly wrong. The distance ladder people thought maybe the CMB people were missing something in their early universe model. The CMB people thought maybe the distance ladder had a wobble somewhere in its lower rungs. Both sides kept checking. The error did not appear. By 2022, when JUST's first CAFIDE results came back and the local measurement held, something shifted, not in the data, in the posture. The question stopped being which side is wrong, and started being what does it mean if neither side is wrong? That is a different question. It requires a different kind of thinking. Discrepancy that survives this much scrutiny is not a problem anymore. It is a result. An unwanted one, maybe. The kind of result that complicates a model that was working beautifully in almost every other respect. But a result. And results, even uncomfortable ones, are information. What the tension is informing us of is still being argued. The candidate explanations fall into a few rough families. There are early universe solutions, modifications to what was happening in the cosmos before and around the time the microwave background was formed. Early dark energy is the most discussed of these, a temporary burst of additional energy density in the early universe that would have slightly altered the sound horizon, the scale imprinted in the microwave background by the ancient acoustic waves, which would in turn shift the H0 value inferred from that background upward, closer to what the distance ladder finds locally. The idea is elegant in outline. In practice, fitting it to the full dataset without breaking other well-measured quantities has been, the word I keep reaching for is fussy. It works in some directions and causes problems in others. There are late universe solutions, modifications to how we understand the local measurement, or to how dark energy has been behaving in the recent cosmic era. These include models where dark energy isn't constant, where it has evolved over the last several billion years in ways that would alter the expansion history and therefore alter what H0 should be at any given moment. DESI's 2024 and 2025 baryon acoustic oscillation results, which preferred a dark energy equation of state that wasn't quite -1, the cosmological constant value, belong to this family of hints, not confirmation, preference, the data leaning in a direction. And then there are the weirder solutions, modifications to gravity itself on cosmological scales, interacting dark matter, new light particles in the early universe, extra neutrino species, or something analogous that would change how fast the universe was expanding before recombination. These ideas are not fringe, they appear in peer-reviewed literature with serious analysis. but they require adding things to the model that have no independent confirmation, which makes physicists nervous in a very specific way. The feeling of solving one equation by introducing three unknowns. The uncomfortable truth is that no single existing explanation resolves the Hubble tension cleanly without creating strain somewhere else in the model. Every proposed fix has a cost. Pull one thread and another tightens. I read a paper once, this is not the most rigorous way to cite something I know, where the authors describe the Hubble tension as cosmology's most vexing problem. That word, vexing, there is something almost domestic about it. Vexing, like a drawer that sticks, like a Wi-Fi router that works fine for everyone else. It has a quality of sustained low-grade irritation that doesn't resolve into either crisis or comfort. The smell of old coffee is apparently what I associate with the hours spent reading these papers. Something about that detail, the mug going cold on the desk, the open PDF, the number that won't move, feels like the right texture for what the Hubble tension actually is to work through. Not dramatic, not sudden, just this persistent, slightly maddening gap between two measurements that are both extremely good. What makes it more than vexing, though? What pushes it past the level of an annoyance into the territory of something important is the sigma. 5 sigma. Let that sit for a second. Particle physics required 5 sigma to declare the Higgs boson a discovery. The detection of gravitational waves from the first binary black hole merger met 5 sigma. These were not quiet anomalies in a filing cabinet. They were new things. The universe had new things in it, and the signal strength was what told us they were real. The Hubble tension has met the same bar. Not for a particle, not for a wave, but for a disagreement. A crack in the model. The crack is real, statistically real, observationally real, confirmed by the methods so different from each other that shared systematic error becomes almost geometrically implausible. JWST using near-infrared imaging of Cepheids in external galaxies. Planck measuring temperature fluctuations in radiation from 13.8 billion years ago. DSE mapping, baryon acoustic oscillations across billions of light-years of galaxy distribution. Gravitational wave sirens, water mazes, surface brightness fluctuations. These are not variations on the same measurement. They're entirely different physical phenomena being used as windows onto the same underlying quantity, and the windows don't quite line up. That is not noise, that is the universe handing us a note. Adam Rees, whose team at Johns Hopkins has been at the centre of the local H0 measurement for years, has described the tension as potentially pointing toward new physics. That phrase, new physics, is one of the most overused in popular science writing, but it has a specific meaning in context. It means physics that isn't in the current model, not a refinement, not a correction, something structurally new, a component, a behaviour, a property of the universe that lambda CDM doesn't contain and cannot explain within its existing framework. The possibility that disturbs the most quietly is evolving dark energy. Not because it's the scariest option, it isn't necessarily, but because of where it leads. If dark energy has been changing over time, then its current value is not the same as its past value. And if it's been changing in one direction, there is no particular reason to assume it has stopped changing. It may be stronger now than it was 1 billion years ago. Stronger than it was last Tuesday. Not measurably so, not in any human timescale, but in principle. And if it's been strengthening, it may continue. The cosmological constant was supposed to be constant. That was the entire point. Empty space with a fixed energy density, stable and unchanging, exerting a steady, gentle pressure that slowly, over billions of years, drives the universe's expansion to accelerate. Benign in a way, the universe expands forever, growing colder and emptier, galaxies eventually vanishing beyond each other's horizons, stars burning out one by one, a long, quiet, very cold ending. If dark energy is not constant, if it grows, the ending is not quiet. That is where the Hubble tension becomes something more than a measurement headache, because the same models that allow dark energy to evolve, that fit the DESI data better than lambda CDM, that might explain why the early and late universe return different expansion rates. Those models include, as one of their parameter spaces, the regime where dark energy crosses what physicists call the phantom divide, where its equation of state drops below -1, where its density does not dilute as the universe expands but actually increases, where the acceleration of expansion is itself accelerating without limit. The Big Rip lives in that regime. I want to be precise here because this is a place where it would be easy to overstate. The Hubble tension does not prove that dark energy is phantom. The DESI anomalies do not confirm it. What they do is keep the door open to a class of dark energy models that includes phantom behavior as a possibility. The data, as of now, is consistent with the cosmological constant. It is also consistent with some evolving dark energy models. It is also consistent with early dark energy solutions that don't involve phantom behavior at all. The error bars are not small enough to discriminate cleanly between these possibilities yet, but they are getting smaller. DESI is still collecting data. Euclid is mapping structure across larger and larger volumes of space. Roman Space Telescope will add supernovae. Rubin Observatory will add weak lensing. In the next 5 to 10 years, the constraints on dark energy's equation of state will tighten considerably. And what those constraints find will either close the door on phantom energy or leave it standing open, maybe open it wider. There is a specific kind of patience that this situation requires. Not the patience of waiting for something to be confirmed, that is ordinary enough. The patience of living with a result that is real and statistically robust and that you cannot yet interpret fully. The tension is evidence of something. The evidence points in a direction. The direction is not yet sharp enough to follow to a specific conclusion. This is not a failure of science. It is just where science is. The model is excellent. The data is excellent. They disagree at 5 sigma in a way that no current explanation resolves without side effects. And the most likely resolution, the general direction in which the hints and preferences and statistical leanings seem to point, is that dark energy is not what we assumed it was, not a constant, something that moves. Whether it moves toward phantom behavior, whether it crosses the divide, whether the expansion rate is not just accelerating but accelerating its own acceleration. These are questions that are answerable in principle. Not tonight, not with the data currently in hand, but with the data that is coming, the telescopes already in the field and the ones being planned. For now, the tension holds. 67 and 73 side by side, neither retreating. A gap too large to be measurement error, too persistent to be luck, too structured to be noise. Something real is hiding inside it, that much is certain. What that something is will determine whether the universe ends slowly, in darkness and cold, or whether the fabric of space itself has a deadline. The cosmological constant has a symbol. Lambda. Lambda. It looks almost like a tent or a doorway, depending on how you hold the idea. Einstein introduced it in 1917, not because the data demanded it, but because without it his equations for a static universe kept wanting to collapse. He needed something to push back against gravity, to hold everything in place. Lambda was that something, a fixed energy density belonging to empty space, constant everywhere and at all times, the same in the early universe as in this moment, the same in the void between galaxies as in the emptiness between atoms, not a substance, a property, the energy of nothing, somehow non-zero, somehow stable. He later called it his greatest blunder. That repudiation had a specific cause, Hubble's observation in 1929 that the universe was not static at all but expanding, and it was hasty in retrospect, because lambda came back. When the expansion turned out to be accelerating in 1998, when Rees and Perlmutter's teams found that distant supernovae were dimmer than they should be in a decelerating universe, physicists reached for the most economical explanation available: lambda, the cosmological constant, a fixed positive energy density in empty space that exerts negative pressure, driving the universe apart at an ever-increasing rate. It fit. It still fits by most measures, but fitting the current data and being correct are not quite the same thing, and the gap between them has been widening in a particular direction. Here is the thing about a constant. It should be the same whenever you measure it. That is the definition. And for a long time we didn't have the tools to seriously test whether lambda was holding steady across cosmic time. We could measure the expansion rate now, roughly. We could measure the temperature fluctuations in the early universe with increasing precision. But the history of the expansion rate, how it changed from epoch to epoch, from the universe's middle age to its present, was not something we could read with much resolution. Baryon, acoustic oscillations changed that. In the first few 100,000 years after the Big Bang, the universe was a plasma, a dense hot mixture of matter and radiation in which pressure waves propagated like sound. Those waves had a characteristic scale, set by the speed of sound and the age of the universe at the moment the plasma cooled enough for atoms to form and the sound to stop. That scale, roughly 500 million light-years in today's units, was imprinted into the distribution of matter across the universe, the way a tuning fork's frequency is imprinted in the air long after the fork has stopped vibrating. And because it is a known scale, it can be used as a ruler. Measure the clustering of galaxies at different distances, which means different times in the universe's past, and you can trace how fast the universe was expanding at each of those times. Deci did this across an enormous volume of space, multiple years of observation, millions of galaxies, redshifts measured with spectroscopic precision, clustering statistics computed at different cosmic epochs. The result was a detailed expansion history, much more granular than anything previous surveys had produced. And when that history was fit to models of dark energy, when astronomers asked what equation of state parameter W would best describe the dark energy required to produce the observed expansion at each epoch, the answer was not quite -1. This is not how it was announced exactly. The language in the papers was careful, as it should be. Preference for dynamical dark energy, hints of deviation from lambda CDM, tension with the cosmological constant at roughly 2.5 to 3.9 sigma, depending on which dataset combination was used. Not 5 sigma, not a discovery, but not nothing either. What the preferred parameter values suggested, in the most commonly used parameterization, written as U0 and WA, for the present value and the rate of change, was something that had been more phantom-like in the past. Equation of state below -1, meaning energy density increasing with expansion, and less so recently, perhaps crossing back above -1 toward the present. A curve, not a flat line, dark energy that moved. The image I keep not quite reaching for, and they're reaching for anyway, is a tide. Not the surface drama of it, the spray and the pull, but the way you notice a tide has shifted. Not by watching it, but by where the waterline is now compared to where it was. You didn't see it move. It moved. The evidence is the position. If dark energy has been changing, we would not have seen it move in real time. No one was measuring the equation of state continuously from the early universe until now. What Deci measured was a set of positions, the expansion rate at several different moments in the past, each translated through a known scale, each carrying its own uncertainty. And from those positions, the outline of a trajectory emerged, not clean, not unambiguous, but curved. A curved trajectory means direction. That is the quiet part of what the DESI results imply, if you take them seriously as a hint rather than a fluctuation. Dark energy has not been sitting still. It has been going somewhere. Where it is going is the part that doesn't have a clear answer. The standard cosmological constant sits at nu equals -1, fixed, serene, unbothered by the expansion it is driving. A dynamic dark energy that started below -1 and is trending back toward it or past it is a different thing entirely. It has a behavior, it has a history, and a thing that has a history can have a future that differs from its present. There is a particular quiet in thinking about dark energy as something that evolves. Not the quiet of resolution, more like the quiet that follows a question after you realize it is bigger than you thought. The cosmological constant was, in a way, a comfortable answer. Fixed. Permanent. A property of the vacuum of empty space itself, like a tax on nothingness that the universe pays in the currency of acceleration. You could understand it without needing to explain it. It was just there, always had been, always would be. A dark energy that changes is harder to hold. It implies a mechanism, something producing the energy, something allowing it to vary, something setting the rate and direction of change. Quintessence models, the most studied class of dynamical dark energy, involve a scalar field, something like a very slow-rolling version of the field that drove inflation in the earliest moments of the universe. The field rolls down a potential energy landscape, and as it does, its equation of state changes. Depending on the shape of the landscape, W can increase or decrease over time. These models are self-consistent. They are also unconstrained in the sense that without knowing the shape of the potential, you cannot predict where the field is going. Some regions of that potential landscape lead to du staying above -1. Normal expansion continued indefinitely, gradually cooling a big fall freeze. Other regions allow W to cross below -1, which standard single-field quintessence cannot do. That requires additional field content, or modifications to the framework, or something called phantom dark energy, where the kinetic term in the field's energy has the wrong sign. Phantom dark energy is theoretically uncomfortable in some ways. It allows for vacuum instabilities, it raises questions about quantum consistency, but it is not ruled out observationally. And the DESI data, when fit to parameterizations that allow phantom crossing, found values consistent with it. Someone left a mug on top of a stack of these papers at some point, and the ring it left bled through 3 pages. That image, not the astronomy, just the stain on the edge of the data, is stuck in my head as the right emblem for how this research actually lives. Not in the clean abstraction of a scalar field rolling down a potential, but in the accumulated hours of people checking the same measurement from different angles and finding that the curve won't flatten. The members who support the Sleepy Physicist are part of why this space exists, and if you'd like to help it grow, the link to our Patreon is in the description. The W sub 0 to W sub A parameterization that DESI used is convenient but not physically motivated. It is a Taylor expansion, a first-order approximation of how W might vary with the scale factor of the universe. It was never meant to be the true equation of state of dark energy. It was meant to be a flexible enough functional form to detect deviation from -1 if deviation exists. And it detected something. Whether that something corresponds to a real scalar field with a real potential, or to an interaction between dark energy and dark matter, or to a modification of gravity that mimics dark energy behavior, the parameterization cannot say. It is sensitive to the shape of the deviation, not its cause. This is the place where cosmology currently lives, downstream of a signal, upstream of an explanation. What would it mean for dark energy to have been strengthening? Not in the most extreme phantom sense, not yet, but simply in the direction of increasing energy density over cosmic time. It would mean that the force driving the expansion of the universe is not a fixed background property, but an active ingredient. Something that changes, something that, having changed in the past, may continue to change in the future. The expansion rate we measure now would be a snapshot of a moving target. The H0 value we calculate from late universe observations would differ from the one inferred from early universe physics, not because of measurement error, but because the physics genuinely changed between those two epochs. The Hubble tension would not be a problem to be fixed. It would be a record of dark energy's trajectory, the early universe reporting one number, the late universe reporting another, and the difference between them mapping the arc of something that has been moving all along. This is speculative. The sigma level is not high enough to call it established, but it is the direction in which several independent lines of evidence are leaning, and the convergence of those leanings, DESY is expansion history, the Hubble tension's persistence, the mild S8 discrepancy in matter clustering, the DESI phantom crossing preference, is the kind of pattern that tends in physics to mean something. Not always. Sometimes patterns dissolve, sometimes they were never there, but sometimes they were. The asymmetry in this chapter's premise, that the past was different from the present and the present from whatever follows, is not a dramatic claim, is actually the most ordinary kind of scientific suspicion, the sense that a thing has changed, derived not from watching it change, but from comparing its position now to its position then, and noticing they don't match. Lambda says they should match. The data says quietly that they don't quite. And if dark energy has a direction, if its trajectory over cosmic time is not flat but curved, then the question of where that curve is going is not abstract. It is the question of what the universe will do next. Whether the expansion rate continues to increase, whether the equation of state remains near -1 or drifts, whether something that has been gently strengthening continues to strengthen, whether the word gently still applies. The DESI data is still coming in. The survey is not complete. The constraints will tighten. The picture, whether it sharpens into a curve or flattens back into a constant, will become clearer. For now, the direction is only hinted at. A slow accumulation. A waterline that has shifted without anyone watching it move. The line is at -1. On one side of it, dark energy behaves. Its density either holds constant or dilutes stosume as the universe expands. Either way, the expansion accelerates. But the acceleration is bounded by what's already there. The energy driving the universe outward does not grow, it is simply present, doing its work against gravity with a fixed supply. On the other side of the line, something different is happening. The energy density does not hold constant. It does not dilute. It increases. As the universe expands and creates more volume, more dark energy fills that volume. not from somewhere else, not transferred from another form, but arising, as if expansion itself were the source. The larger the universe gets, the more energy it contains. The more energy it contains, the faster it expands. The faster it expands, the more energy it contains. This is phantom energy, and the line between it and everything else is a single number, W equals -1. The equation of state parameter W is just a ratio, pressure divided by energy density, adjusted for units. For ordinary matter, W is 0. Matter has energy density but no significant cosmic pressure. For radiation, W is 1/3. For dark energy as a cosmological constant, W is exactly -1. The pressure is negative and equal in magnitude to the energy density, which is the mathematical condition that keeps the density constant as space expands. The negative pressure does work on the expanding volume that exactly replenishes the energy lost to the expansion. Balanced, precise, static. Below -1 the balance tips. The negative pressure exceeds the energy density in magnitude. More work is done on the expanding volume than could be accounted for by simple conservation in the usual sense. The density rises, and the Friedmann equations, the equations that govern how the universe expands, respond to rising density with rising expansion rate. Not just acceleration, accelerating acceleration. In the W equals -1.5 scenario that Caldwell, Kamionkowski, and Weinberg worked through in their 2003 paper, the universe reaches the point of total structural disintegration in roughly 22 billion years. That number is specific to that value of W change due to -1.1, and the timeline stretches enormously, hundreds of billions of years. Change it to -1.01, and the Big Rip recedes toward the practically infinite. The closer you sit to -1, the longer before anything catastrophic occurs. But the direction of the inequality still matters. Below -1 and you're in phantom territory, regardless of how far below. What Caldwell named phantom energy in that paper was partly a provocation. He knew it was theoretically uncomfortable, knew that a field with U less than -1, modelled as a scalar field in general relativity, requires a kinetic term with the wrong sign. Negative kinetic energy. A ghost field in the terminology. Ghost fields introduce instabilities. The vacuum can decay. Energy can be extracted from it without limit. Quantum corrections blow up. These are not small concerns, and yet the paper was published, it was not dismissed, because the observational data at the time, and more so the data since, did not rule out W less than -1, still doesn't. The Planck satellite's best fit value for W is -1.028, with an uncertainty of plus or minus 0.031. That central value sits on the phantom side of the line. The error bars straddle it. You cannot conclude from that number that phantom energy exists, but you cannot conclude from it that it doesn't. There is something almost stubborn about how phantom energy has persisted in the literature since 2003. It arrived uninvited, introduced as hypothetical with acknowledged theoretical problems, and it never left. Not because physicists decided to embrace it. Most would prefer clean, well-behaved dark energy with U comfortably above -1. But because the data kept returning values near -1, and near does not mean above, models that allow phantom crossing, that allow W to drift below the line, even temporarily, continued to fit the observations as well as, or better than, the cosmological constant. Deasy's results in the 2024 and 2025 did not change this picture so much as deepen it. The preferred W0 to WA values from the baryon acoustic oscillation data, combined with supernova and CMB datasets, sat in a region of parameter space consistent with a dark energy that had crossed below -1 at some point in the recent cosmic past. Not decisively. The error contours were large enough to include the cosmological constant, but the central value, in multiple analyses using different dataset combinations, landed on the phantom side. The hum of a hard drive, late, the particular quality of reading numbers that don't care what you prefer them to say. The theoretical discomfort with phantom energy has not gone away, but several approaches have been developed that can produce effective phantom behavior without the ghost field problems. In some models, an interaction between dark energy and dark matter produces an effective equation of state below -1 without requiring negative kinetic energy in the dark energy field itself. In modified gravity frameworks, the geometry of spacetime can mimic phantom behavior without invoking phantom fields directly. These are not proven mechanisms. They are existence proofs, demonstrations that hour less than -1 can emerge from physically consistent theories, which means the observational preference for phantom-like behavior does not require accepting theoretically bankrupt physics. It requires accepting that the universe might be doing something we haven't fully characterized yet. That is, at its core, what sitting with phantom energy requires. Not belief in it, not dismissal of it. The data neither demands it nor excludes it. What the data does is keep the door open, the same door it has been keeping open since 2003, a little wider now than it was then, with more locks removed, but still not through. What would change if dark energy has been phantom all along, even mildly? W at -1.01 or -1.03, well within current error bars, barely distinguishable from a cosmological constant by any instrument we currently have. The universe would be a slightly different place from the one the standard model describes, not yet visibly different, not in any way that a human lifetime, or 1,000 human lifetimes, could observe directly. The expansion rate would be fractionally higher than lambda sig dm predicts. The energy density of empty space would be fractionally growing. The acceleration would be accelerating by an amount too small to measure with certainty but mathematically present, and it would compound, slowly at first, then faster. There is no ceiling on the other side of -1. That is the thing about phantom energy that sits in the room and doesn't leave. Every other form of energy has some eventual limit on its influence. Matter dilutes, radiation dilutes. Even a cosmological constant reaches a steady state where its influence is fixed. Phantom energy has no such limit. It grows with the universe it is expanding. The larger the universe, the stronger the force driving it to expand further. The further it expands, the stronger the force becomes. There is no equilibrium in that direction, only continuation toward whatever the mathematics finds at the end of a runaway curve. The Hubble tension has mostly been treated as a problem about the past. Two ways of measuring the expansion rate, returning different answers, and the disagreement centered on which description of the early universe is correct, or which calibration of the distance ladder is accurate, or what property of the cosmos between then and now is being misrepresented by the standard model. The argument has been backward-facing. What went wrong in the accounting? Where the error entered? But there is another way to face the same discrepancy, not toward its origin, but toward its implications. If the gap between 67 and 73 kilometers per second per megaparsec is not a measurement problem, if it is a signal encoded in the difference between two accurate and well-calibrated results, then it is telling us something about what dark energy has been doing between the early universe and now. And a dark energy that has been doing something is a dark energy that may continue doing it. That continuation is what this chapter is about. The logic is not complicated, though it is easy to understate. If the early universe, described by Planck's microwave background data, predicts a present-day expansion rate of 67, and the present-day universe, measured directly through Cepheids and supernovae, returns 73, then the expansion rate has grown more than the standard model expected it to. Lambda CDM, with its fixed cosmological constant, predicts a specific expansion history, a curve that describes how H changed from the Big Bang until now. The local measurement sits above that curve at the present end, which means the actual expansion history, whatever it is, bends higher than the predicted one in the recent cosmic era. A higher than expected expansion rate in the recent universe is consistent with dark energy that has been strengthening. Not the only explanation, but a consistent one. And if dark energy was strengthening in the recent past, the last few billion years, then the question of whether it is still strengthening now, tonight, at whatever rate the universe is actually expanding at this particular moment in its history, is not answerable with certainty. But the direction of the data does not argue against it. This is the quiet part, the part that tends to get lost in the discussion of the tension as a measurement puzzle. A slow current is only visible if you watch the water long enough. Set a leaf on the surface and come back in an hour, and you can trace the direction of flow from where the leaf has gone. You did not see the current move, you saw its effect accumulate. The expansion history is something like that leaf's trajectory, a record left in the positions of galaxies, in the clustering of matter, in the dimness of distant supernovae, in the scale of baryon acoustic oscillations at different epochs. Desai read that trajectory across a volume of space, spanning billions of light years and multiple cosmic eras. The trajectory it found was not flat. The dark energy equation of state, in the models that best fit the data, was not a constant line at -1. It curved. It had a shape. A curved trajectory is a history of direction, and a direction continued is a prediction. The particular shape that the DESI data preferred, in the DU0 to WA parameterization, the most commonly used framework for describing evolving dark energy, had you below -1 in the earlier portion of the recent cosmic era, trending back toward or past -1 in the more recent period. There is genuine uncertainty in these values. The error bars are not small. The cosmological constant sitting at W equals -1 always remains within the allowed range of most dataset combinations. No one is claiming that Desai has proven dynamic dark energy, but the preferred values point somewhere, and what they point toward in one reading of the data is a dark energy that was more phantom-like in the past and is evolving toward something less extreme now, or possibly past -1 again, depending on which analysis you trust and which datasets you combine. The trajectory is not simply dark energy is getting stronger and will keep getting stronger. It is messier than that, which is, if anything, more disconcerting. A neat trajectory would be easier to extrapolate. A curved, uncertain one is harder to follow to its end. The ceiling of a room I once worked in had a water stain that grew by almost nothing each week, barely visible month to month. You only noticed it by comparing the edge to where it had been the winter before. That is the register at which dark energy, if it is evolving, is currently operating, too slow for any human timescale to observe as change, only visible as difference when you compare measurements made at vastly different epochs. What would the Hubble tension look like, reframed as a forward-pointing statement rather than a backward-pointing puzzle? It would look like this. The universe has been expanding faster in the recent era than the early universe model predicted, and one class of explanations for that excess involves dark energy that has been active, not static, not inert, but doing something in the last several billion years. If that activity continues, the expansion rate tomorrow will be slightly higher than the expansion rate today. Not measurably higher in any human sense, but higher. And the tomorrow after that will be slightly higher than that one, and so on, compounding across cosmic timescales, until the difference between the expansion rate now and the expansion rate in 10 billion years is not slight at all. This is not a dramatic claim, it is arithmetic. A quantity that increases without ceiling will, given sufficient time, reach values that make the current expansion rate look negligible. The question is only whether dark energy is that kind of quantity, whether it has a ceiling, whether the trajectory curves back, levels off, or continues. The data does not currently answer this. The uncertainties are wide enough to contain several different futures, but the question is physically real, and the Hubble tension is one of the places where it surfaces in the observational record, not as a prediction of catastrophe, but as an unexplained excess that demands some accounting. The accounting that involves phantom energy is the most structurally significant one, because it is the only class of explanation that leads not just to continued expansion, but to runaway expansion. In a phantom dark energy universe, the expansion rate does not asymptote to some steady high value. It increases without bound. The Hubble parameter, which describes the rate of expansion per unit distance, grows toward infinity in finite time, and as it grows, the distance over which any physical interaction can occur shrinks. Gravity, electromagnetism, the strong nuclear force, all of these operate across distances. When those distances become smaller than the structures held together by the forces, the structures come apart. This is not the slow cooling of a big freeze, it is a different kind of end. More sudden, in the cosmic sense, though sudden, here still means billions of years away, under most phantom models with W near -1. The structural failure happens on a schedule determined by how far below -1 the equation of state sits. W equals -1.5 gives roughly 22 billion years. W equals -1.1 gives something much longer. W equals -1.0. One pushes the end so far into the future that it becomes practically indistinguishable from never, at least on any scale we can currently reason about. But the direction is the same regardless. Below -1, the trajectory points at a singularity. The Hubble parameter grows without stopping. Everything that is bound by any force at any scale eventually finds that the expansion has grown large enough to unbind it. The Hubble tension, read forward rather than backward, is a possible early signal of this. Not proof, not even strong evidence, but a persistent multi-method 5 sigma discrepancy that is consistent with dark energy that has been strengthening in the recent cosmic era is also consistent with dark energy that will continue to strengthen. The two things are not the same claim, but they live in the same region of parameter space. If dark energy has a direction, if the DESI data is hinting at something real, if the Hubble tension is not error but signal, then what we are measuring right now with our best telescopes and most careful analyses is the early accumulation of a process that may not stop. That word, may, is doing a lot of work in this chapter, has been doing a lot of work in this entire conversation. The uncertainties are genuine. The alternative explanations are real. The cosmological constant might be exactly right. The Hubble tension might resolve into some combination of early universe modifications that don't involve phantom behavior. and the universe might end slowly and coldly and without structural catastrophe for hundreds of billions of years. All of that is possible. The data does not rule it out, but the data also does not rule out the other reading. And the other reading is that the gap between 67 and 73 is a record of something that has been moving in a particular direction for a long time, without announcing itself. The way a current moves without making noise, visible only in where things end up after travelling through it long enough. Where things end up in that direction is something the next few chapters follow more closely. The measurement sits, the gap stays open, and somewhere in the difference between two careful, accurate numbers, something about the long future of everything may already be written. Start with something simple. The universe has a size, not in the sense of having an edge. It may not have one, and whether it does is a separate question from the one this chapter is following, but in the sense that any 2 points in the universe can be described as being some distance apart, and that distance changes over time as the universe expands. The scale factor, written as a t in cosmological notation, is a way of tracking that change without fixing a particular distance. It is defined relative to some reference moment, usually taken as the present, where a equals 1. At earlier times, when the universe was smaller and everything closer together, a was less than 1. At future times, as the universe expands, a will be greater than 1. That is all it is at the level of definition, a dimensionless number that grows. What makes it interesting? What makes it the right thing to watch in a phantom energy universe is what governs how fast it grows. The Friedmann equations, derived from general relativity, describe the relationship between the expansion rate and the energy content of the universe. More energy density means faster expansion. And in a phantom energy scenario, where the energy density of dark energy increases as the universe expands, you get a feedback loop of a particular kind. The scale factor grows, which means the volume grows, which means, in a phantom universe, the energy density grows, which means the expansion accelerates, which means the scale factor grows faster. There is no equilibrium in that loop. In a universe with a cosmological constant, the standard lambda CDM picture, the scale factor grows exponentially but smoothly. The expansion accelerates, yes, but it does so at a rate that itself remains bounded. The Hubble parameter h, which describes the fractional rate of expansion per unit time, approaches a constant value determined by the energy density of the cosmological constant. Asymptotically, the expansion rate does not keep increasing indefinitely. It levels off at a fixed high value and stays there. The scale factor grows without bound in the sense that it never stops climbing, but it climbs at a rate that becomes constant, a steady, smooth, ultimately boring curve extending to infinity. In a phantom universe, h does not approach a constant. It grows. The Hubble parameter increases without ceiling, and in the Friedmann framework, a growing h means a growing expansion rate, which means a growing rate of growth of a t. The scale factor accelerates not just in the ordinary sense, but in a compounding sense. Its rate of increase is itself increasing, and the rate of that increase is increasing too, and so on, all the way up. Mathematically, what this produces is a specific kind of singularity, not the kind at the Big Bang, where the scale factor was 0 and density was infinite. That singularity was at the beginning, where everything compressed to a point. The Big Rip singularity is the opposite. The scale factor reaches infinity in finite time. The Friedmann's equations, when solved with phantom dark energy, produce a solution where A of t diverges, reaches infinity at a specific moment in the future. The time to that divergence depends on the equation of state parameter W and the current value of the Hubble constant. But for any W below -1, no matter how close to -1, the divergence occurs at a finite time, not eventually, not asymptotically. At a specific moment, the mathematics hits a wall, or rather, the mathematics goes through the wall. Reality hits it. The phrase reaches infinity is doing something slippery here that is worth pausing over. In mathematics, infinity is a limit, a behavior, a direction of travel rather than a destination. You can talk about a function diverging to infinity without that statement implying that infinity is a place the function arrives at. The scale factor in a phantom universe grows without bound. Technically, that is the precise statement. The divergence is a finite time singularity, which means that at some moment in the future, no finite value of a t satisfies the equations, and the mathematical framework that produced the solution breaks down. This is the point where the equations stop describing reality, because reality as we know it, matter, forces, structure, the physical laws themselves, has already ended. The mathematics breaks not because it is wrong, but because it runs out of things to describe. The pencil on the desk, the one with the chewed eraser, the one that has been sitting at the same angle since this morning. That kind of ordinary object helps, somehow, with what comes next. Not because it's connected to the physics, but because it is a thing held together by forces. The wood fibers are held together by molecular bonds. The graphite is a lattice of carbon atoms held together by covalent chemistry. The plastic of the eraser is a polymer chain, held together by the same electromagnetic force that holds everything made of atoms together. It exists as a coherent thing because the forces that bind its parts are stronger than anything currently pulling them apart. What the scale factor's climb does, in a phantom universe, is change that balance. Not directly. Not by reaching into the pencil and grabbing, but by making the universe expand fast enough that the distance between any 2 points is increasing at a rate the forces between them cannot accommodate. The electromagnetic force does not have infinite range. Gravity does, technically, but in an expanding universe, objects beyond a certain distance, the Hubble horizon, cannot communicate through gravity because the space between them is expanding faster than gravity can propagate. As the Hubble horizon shrinks, which it does as h grows, structures find themselves cut off from the forces that were holding them together. This is the mechanism of the Big Rip. Not a direct assault on matter, but a progressive isolation. Each structure becomes an island, then a shrinking island, then an island too small to contain itself. The sequence is determined by which forces are weakest at which scales. Gravity is the weakest force and operates at the largest scales, which is why the first structures to fail are the largest ones. Galaxy clusters, held together by the collective gravity of billions of galaxies and enormous quantities of dark matter. Their binding is real but relatively loose, and loose bindings fail first. The Caldwell-Kamienkowski and Weinberg calculation from 2003 worked this out for a specific case. W equals -1.5 H0 equals 70 kilometers per second per megaparsec. Matter density at roughly 30% of critical. Those numbers produce a big rip approximately 22 billion years from now. Within that 22 billion year window, the sequence of structural failures can be calculated from the scale factor's behavior at each stage. Galaxy clusters begin to feel the strain roughly 200 million years before the end. The scale factor at that point has grown enough that the Hubble parameter is encroaching on the scales at which cluster gravity operates. The clusters don't explode, they just stop cohering. The member galaxies drift outward and don't come back. The cluster is no longer a cluster, it is a dispersal. 60 million years before the end, individual galaxies begin to fail. The Milky Way, whatever remains of it by then, merged with Andromeda earlier by roughly 4 billion years from now, would find its stars drifting outward, the gravitational well of the combined galaxy flattening as the Hubble parameter on galactic scales overtakes the escape velocity. Loosely bound outer stars go first. Then the disk thins. The center holds longer because the density is higher and the gravitational binding stronger, but the center cannot hold indefinitely. 3 months before the Big Rip singularity, the solar system fails. 3 months, that is a specific and somewhat strange number to sit with. The universe has existed for 13.8 billion years. In the last 3 months of its coherent existence, our solar system, if it still exists, which it won't, but in principle, would lose the gravitational binding that keeps planets in orbit. The distance between the Sun and the Earth would begin to grow, not because anything pushed them apart, but because the expansion of space itself, at that point growing at an astronomical rate per unit distance, would overcome the Sun's gravitational pull at orbital distances. 30 minutes before the end, stars and planets cease to hold together as objects. The matter that composes them is still there, the atoms, the nuclei, but the gravitational and molecular forces that make a planet a solid thing and a star a contained fusion reactor are no longer sufficient. The objects disperse. 10 to the power of negative 19 seconds before the singularity, a number so small it has no intuitive scale, far smaller than any time scale at which known physics operates normally, atomic nuclei dissociate. The strong nuclear force, which is genuinely strong by any measure, holds protons and neutrons together against enormous repulsive forces at ranges of about 1 femtometer. But the expansion rate at this point has exceeded even those scales. Nuclei come apart, protons and neutrons separate. Electrons had already been stripped from atoms before that. Ionization comes earlier, because electrons orbit at larger radii than nuclear scales, and the expansion reaches atomic orbital distances before nuclear ones. At the singularity itself, the scale factor is formally infinite. The Hubble parameter is infinite. The density of phantom dark energy is infinite. And the mathematical description of the universe as a manifold with a metric, as space-time, as the setting in which physics occurs, breaks down. What does it mean to watch a number climb toward a value it can never actually reach, except that it does? I keep turning this over. The honest answer is that it means the number is not a number in the ordinary sense, and the thing it's describing is not a thing in the ordinary sense. The scale factor in a phantom universe is not like a speedometer climbing toward a red line. It is more like, and I want to be careful here because this comparison is imperfect, the temperature of a thing approaching absolute zero in reverse. Approaching a state that the laws describing normal behavior cannot accommodate, where the description language exhausts itself before the thing it's describing does. What the scale factor does is climb, steadily, then faster than that, then faster than you have a way to say faster than that about, until the rate of climbing is itself climbing faster than any finite description can follow. And at the moment the description fails, not before it, not after it, precisely at the moment, the physical processes that generated the description, that made observation and measurement and mathematics possible, have already ceased. The universe doesn't end and leave the equations intact. The equations end with it. There is no perspective from which the singularity is observed. There is no moment after it. The scale factor reaches infinity in the only way it can, by making the framework that defined it obsolete. Whether this is what the universe will actually do depends, as everything in this territory depends, on what dark energy turns out to be, on whether the DESI hints solidify into confirmation, on whether the Hubble tension resolves into a signal or dissolves into systematics, on whether W stays at -1 or has been drifting below it for longer than we know. The scale factor is climbing right now. That much is certain. Every galaxy cluster, measured and unmeasured, is moving away from every other, and the rate at which they separate is increasing. Whether that increase will remain bounded, or will itself accelerate past any bound, whether the climb is heading for a plateau or a singularity, is the question that the next several decades of cosmological measurement may begin to answer. For now, the number grows, quietly without announcement at every moment, and in the mathematics of phantom cosmology, it knows where it is going even if we don't yet know whether the mathematics describes us. The night sky is already a lie, in the gentlest possible sense. Every star visible from the ground is showing you the past. The light from Proxima Centauri, the nearest stellar neighbour, left its source 4 years ago. The light from the stars of the Orion constellation has been travelling for hundreds of years, some of it for thousands. The Andromeda galaxy, faintly visible to the naked eye as a smear of dim light in the right conditions, is showing itself as it was 2.5 million years ago. When you look up, the sky is not a picture of one, it is a collection of messages from different depths of the past, all arriving simultaneously, all pretending to be present. This is not a problem. It's just how light works. It has a speed, and distances are large, and the delay accumulates. Under ordinary cosmic conditions, meaning conditions where the expansion of the universe is accelerating but doing so at a bounded rate, most of the stars we can see are close enough that the delay is manageable, and the Milky Way itself is so much closer than everything else that the sky retains something like coherence. The stars are ours, in a loose sense. They are reachable in principle, even if not in practice. What phantom energy does to the sky is something different from simply making stars more distant. It changes what it means for a star to be visible at all. There's a boundary in cosmology called the Hubble horizon, or the Hubble sphere, the distance beyond which the space between us and a given object is expanding faster than the speed of light. This does not violate relativity. Nothing is moving through space faster than light, but the space itself is growing, and that growth can outpace any signal. Objects beyond the Hubble horizon cannot send us light that will ever reach us. The expansion carries it back faster than it can travel forward. Those objects exist. We simply cannot receive anything from them. Under the standard cosmological constant model, the Hubble horizon grows over time. The observable universe expands. We gradually come to see light that was previously beyond our reach, though the objects that emitted it are now even farther away. The universe goes dark eventually. In the very far future, when all the stars have burned out and galaxies have dispersed, and the cosmos has reached its maximum entropy. But that darkness is a different kind. A darkness of exhaustion rather than isolation. In a phantom energy universe, the Hubble horizon does not grow, it shrinks. As the Hubble parameter h increases, as dark energy strengthens and the expansion rate climbs, the distance at which recession velocity equals the speed of light gets smaller. The sphere of influence around any observer contracts. Not quickly at first. In the early phantom era, the shrinkage is slow enough that it would take billions of years to notice, but the direction is set from the beginning. Every year, the observable universe is a little smaller than it was. Every year, there are objects, galaxies, galaxy clusters, entire walls of large-scale structure that were visible last year and are not visible this year, not because they moved, but because the expanding space between us and them now carries their light away faster than it can approach. The first thing to disappear will not be the farthest galaxies. They are already gone, in the sense that they have long since passed the Hubble horizon of the Standard Model. The things that will disappear in the Phantom Era are the things that were still inside the horizon, the nearby galaxy clusters, the members of the local group, eventually Andromeda. This will take an enormous amount of time, billions of years. The precision depends on the value of W, and on how long the phantom behavior has been active. But even in aggressive phantom scenarios, the isolation of our local group from the broader cosmic web of galaxies takes on the order of billions of years. There is no sudden darkness. There is a very slow dimming across timescales that dwarf everything that has happened in the universe so far. The tea has gone cold, the way it always does when you sit too long with one thought. Some small domestic betrayal of how much time actual thinking takes. There is something appropriate about that here. What the very long quiet looks like from inside it is almost nothing. Stars are still burning. Planets, where they exist, still orbit. Chemistry still works. The atoms that make up everything still cohere. Gravity still draws matter together locally. The expansion of space does not undo local gravitational binding until the Hubble parameter has grown considerably larger than it is now. So the long quiet before the end is not, by most ordinary measures, distinguishable from the present. It is only distinguishable by what is missing, by the signals that no longer arrive, by the sky. The research notes for this video are available on Patreon. The PDF includes common misconceptions, fun facts for the curious, and much more. The link is in the description. The night sky in a phantom universe billions of years into the quiet would be a different thing from the one outside any window tonight. The galaxies beyond the local group, the Virgo cluster, the Perseus cluster, the vast filaments of the cosmic web would have passed beyond the shrinking horizon long before. Even within the local group, which is gravitationally bound tightly enough to resist the expansion for a very long time, the galaxies would eventually thin. The light from what was once an observable universe of 2 trillion galaxies would have been replaced by the light from a handful, then fewer. An observer in that era, if such a thing could exist, which is a separate question, would look at the sky and see a much simpler picture than we see. Fewer sources, wider silences between them. The background glow of the cosmic microwave background, already cold and faint by our era, would have redshifted further into the undetectable. The radio universe would have gone quiet. What remained visible would be local, close, known, and surrounded by a darkness that contained things, but things that could no longer speak. This is not silence in the acoustic sense. Space is silent already. It is silence in the informational sense. The absence of arriving signals, the cessation of incoming light, the condition of being unable to receive any message from the rest of the universe because the rest of the universe has moved beyond the range at which messages can be sent. The physics of the structures left behind would not change immediately. Atoms still behave as atoms. Stars still fuse hydrogen in their cores for as long as their hydrogen lasts. The long quiet is not destruction, it is isolation. And isolation, at cosmic scales, looks almost indistinguishable from ordinary existence. except that the sky is darker and darker, and the silence where signals used to arrive grows wider with each passing era. It is worth staying here, in this long middle stretch, before the sequence of failures that follow. Not because the quiet is dramatic, it isn't, but because it is the actual experience of a phantom universe in the eras that most resemble our own. Billions of years of ordinary physics, in a cosmos growing progressively more alone, galaxies still forming stars, matter still gravitating, the local universe still coherent, still busy, still doing what matter does when left to its own interactions, and all the while the scale factor climbing, the Hubble parameter growing, the horizon contracting by amounts too small to measure from one century to the next, but accumulating across deep time into something that will eventually matter enormously. The end does not announce itself from across the quiet. It simply arrives, one structural threshold at a time, after a stillness so long that the stillness came to feel like the whole story. It wasn't, but the quiet was real. It lasted longer than anything else. Galaxy clusters are the largest gravitationally bound structures in the universe. Not individual galaxies, not solar systems, not anything on a human scale. Clusters, which contain hundreds to thousands of galaxies along with enormous quantities of dark matter and hot intracluster gas, all held in a loose gravitational embrace that can span tens of millions of light years. The Virgo cluster, the nearest large one to us, contains more than 1,000 galaxies. The Coma cluster contains thousands. These structures formed over billions of years, matter falling into the gravitational wells carved by dark matter, galaxies accumulating like sediment. They are not fragile. Gravity at those scales is patient and deep, but in a phantom universe, gravity at those scales is what fails first. Roughly 200 million years before the Big Rip singularity, under the Caldwell et al. Parameters of W equals minus 1.5, which gives a total time of about 22 billion years from now, the Hubble parameter has grown to the point where the recession velocity at the scale of cluster diameters exceeds the gravitational escape velocity that holds the cluster together. Not all at once. The most loosely bound members, the galaxies at the cluster's outermost edges, the ones with the weakest gravitational tethering begin to drift outward and fail to return. The cluster doesn't explode, it thins, the outer galaxies separate. The core persists longer, because the gravitational binding is stronger where the density is higher, but the outer structure dissolves, and what was a cluster becomes, over the following millions of years, a scatter of galaxies no longer in any meaningful gravitational conversation with each other. The local group, the gravitationally bound collection that includes the Milky Way, Andromeda, and several dozen smaller galaxies, would experience a similar dissolution. By this point in the timeline, Andromeda and the Milky Way will have already merged, billions of years prior, into a single large elliptical galaxy that some people have taken to calling Milkdromeda, which is a name that will probably not survive the merger itself. Whatever the merged galaxy is called, it holds together through ordinary gravitational dynamics for a very long time. But 200 million years before the end, the expansion rate at its scale becomes significant. The outermost stars begin to leave. The tidal forces of the expanding spacetime work at the galaxy's periphery first. 60 million years before the singularity, individual galaxies begin to fail. The Milky Way, or rather the merged remnant of it, would find its disk structure unstable. Stars in the outer disk, which orbit the galactic center at distances of tens of thousands of light years, would find that the centripetal force provided by the galaxy's gravitational well is no longer sufficient to maintain those orbits against the expansion. This is not a sudden event. A star does not simply stop orbiting and fly outward in a straight line. The process is gradual, the orbit widening and becoming less bound over time, until the star's velocity with respect to the galactic center exceeds the local escape velocity, and it does not return. The stars leave, not in a group, not in a rush. Individually, the most loosely bound first, then progressively more tightly bound stars as the Hubble parameter continues to climb. The galaxy, which once contained hundreds of billions of stars in a structure with genuine coherence, a disk, a bulge, a bar, spiral arms, becomes first a looser collection and then a dispersal. The gravitational binding that made it a galaxy, rather than a coincidental gathering of stars, simply stops being sufficient. Something about the image of a star leaving its galaxy without drama, just drifting outward on a widening path until the path becomes a departure, is specific in a way that's hard to place. Not just specific. 3 months before the end. The solar system, or whatever remains of a planetary system by this point in the timeline, stellar evolution will have transformed the Sun into a white dwarf long before the Big Rip arrives. Assuming a 22 billion year timeline, would lose its gravitational coherence. The planets in their orbits would find the effective gravitational well of the central star unable to maintain those orbits against the expansion. The outermost planets go first. Neptune's orbit, which takes 165 years to complete, is the most loosely bound, and a loosely bound orbit is the first to fail. Then Uranus, then Saturn, then Jupiter. The inner planets hold longer because they orbit closer to the star, and the gravitational binding at shorter distances remains stronger for longer. 3 months. The entire sequence of planetary orbital failure, from the outermost gas giants inward to the rocky inner planets, compressed into a span of time that by any ordinary measure is nothing. Less than a season. The universe spent 13.8 billion years building and maintaining the structures that constituted planetary systems, and the process by which those systems fail occupies a few months at the end. The Hubble parameter by this point has grown to values that make the current expansion rate look negligible. The rate of change of the scale factor is enormous. The rate of change of that rate is enormous. The numbers are formally accessible through the Friedmann equations, but their physical intuition is almost lost. The universe at this point is expanding at rates that have no human-scale analogy. 30 minutes before the end, stars and planets cease to be objects in any useful sense. A star is a contained fusion reactor, an ongoing competition between the outward pressure of radiation from nuclear reactions in the core and the inward pressure of the star's own gravity. This balance, maintained over millions to billions of years, is what makes a star, rather than just a very large hot cloud of gas. A planet is a ball of matter held in shape by the pressure balance between its own gravity and the material strength of its interior. Both structures depend on gravity to maintain their coherence. At 30 minutes before the Big Rip, the Hubble parameter on stellar and planetary scales has grown large enough that the expansion overcomes the gravitational self-binding of these objects. The matter of a star, which was already by this point whatever end-stage remnant remained after nuclear burning disperses. The atoms are still there. The particles are still there. But the structure they made, the thing that was, in any earlier era, a star or a planet or a moon, is no longer a structure. It is a cloud of atoms in a universe expanding faster than gravity can draw them back together. Nothing burns at this point. There is nothing left to burn, and the timescale is too short for any nuclear process to matter. The dispersal of matter to beam stars is simply dispersal. Material that spent billions of years held together by gravity becomes, in 30 minutes, a scatter of atoms in an expanding void. Minutes. The atoms disperse in the expanding space. Each atom, hydrogen, helium, carbon, oxygen, iron, whatever elements the long history of stellar nucleosynthesis produced over the universe's prior billions of years, is now moving independently through a universe expanding so fast the distance between any two atoms is growing faster than any force between them can operate at ordinary ranges. But atoms are not the smallest structural unit. An atom is a nucleus. Protons and neutrons bound together by the strong nuclear force at scales of about 1 femtometer, surrounded by electrons held in their orbitals by the electromagnetic force at scales of angstroms. The electromagnetic force has a much longer effective range than the strong force, but it is weaker, and the strong force, though far stronger at nuclear scales, operates only at those scales. What happens as the expansion rate climbs through the final minutes is not, initially, nuclear. It is electromagnetic. The electrons of each atom occupy orbitals at distances far larger than the nucleus, roughly 100,000 times larger. If you scaled the nucleus to the size of a marble, the electron cloud would extend to roughly 2 kilometers. The electromagnetic force that holds electrons in those orbitals is being competed against by an expansion rate climbing through length scales from the largest to the smallest. The electrons go first. At some point in the final minutes, the exact timing depends on the atomic species and orbital shell. The expansion rate at the scale of electron orbitals exceeds the electromagnetic binding energy per unit distance. Electrons are no longer held, they depart. The atoms ionize, not through thermal collision, not through radiation, but through the expansion of space-time itself, pulling the electron away from the nucleus it belonged to. What remains at that moment is a universe of bare nuclei and free electrons, separated from each other and moving apart in a space expanding at rates no physical force can oppose. 10 to the power of minus 19 seconds. 1/10 of a second before the Big Rip singularity, the expansion rate reaches the scale of atomic nuclei. It's genuinely difficult to hold as a timescale. The Planck time, which is the smallest interval at which current physics maintains any meaning at all, is roughly 10 to the power of minus 43 seconds. The timescale of strong nuclear interactions, the processes by which quarks exchange gluons and hold protons together, is on the order of 10 to the power of minus 23 to 10 to the power of minus 24 seconds. The moment of nuclear dissolution in the Big Rip, at 10 to the power of minus 19 seconds before the singularity, is far longer than those interaction timescales, but it is the point at which the Hubble parameter on nuclear scales, the expansion rate measured across distances of 1 femtometer, exceeds the strong force's ability to maintain nuclear binding. Protons and neutrons separate. The strong nuclear force which had held them together since the first minutes after the Big Bang, across the entire history of the universe, stops being sufficient. Not because the force weakens, it doesn't, but because the space between them is expanding faster than the force can operate across it. And then the nucleons themselves. The quarks inside each proton and neutron are confined by the strong force. Color confinement means a single quark cannot exist in isolation under ordinary conditions. At the scales and timescales involved in the final moments before the singularity, the physics of quark confinement under extreme expansion is not fully resolved by any current theory. Whether quarks are individually freed, or whether the singularity simply arrives before any clean nuclear-to-quark transition can be described, this is genuinely unclear. The singularity does not wait for the physics to be tidy. At the moment of the Big Rip, the scale factor is formally infinite. The Hubble parameter is formally infinite. The energy density of phantom dark energy, which has been growing throughout the phantom era, is formally infinite. The space-time manifold, the mathematical structure that general relativity uses to describe the geometry of the universe, is singular. The equations that produce the timeline that calculated the 200 million years and the 60 million years and the 3 months and the 30 minutes and the 10 to the minus 19 seconds no longer have a solution. There is no moment after the singularity described by the same mathematics. Whether there is a moment after it described by some other mathematics, some framework beyond general relativity, some quantum gravity theory in which singularities are resolved rather than terminal, is an open question, one that the current state of physics cannot answer. What can be said is what the sequence looked like from the outside of any given structure, watching it fail. Not catastrophic in the usual sense, not violent in any way that the word violence ordinarily implies, but simply insufficient. Each binding at each scale, reaching a moment where it was no longer enough. Gravity at cluster scales, gravity at galactic scales, gravity at stellar scales, electromagnetism at atomic scales, the strong force at nuclear scales. Everything holds until it doesn't, and it doesn't in that order, over that sequence of timescales without exception. Physics is a description. That is worth saying plainly before anything else. It is not the thing itself, not the force, not the particle, not the geometry, but a set of mathematical relationships that models how those things behave under conditions we've observed and tested. General relativity describes gravity and the large-scale structure of space-time with extraordinary accuracy across an enormous range of conditions. Quantum mechanics and quantum field theory describe the behavior of matter and energy at small scales with equal or greater precision. These are the two main pillars, and between them they cover essentially everything we can measure or observe in the physical world. The problem is that they are incompatible with each other, in a technical sense that physicists have been working on for most of a century without resolution. General relativity treats spacetime as a smooth, continuous manifold, a geometry that can curve and stretch in response to energy and mass, but that is always well-defined, always differentiable, always a surface on which physics can operate. Quantum mechanics treats everything as fundamentally discrete and probabilistic, governed by uncertainty principles that set hard limits on how precisely certain pairs of properties can be simultaneously known. When these two frameworks are applied together, when you try to describe a situation where both extreme gravity and extreme quantum effects are simultaneously important, the mathematics produces results that are not physically meaningful. Infinities appear in places where finite answers are required. The frameworks contradict each other. Most of the time, this incompatibility does not matter. Gravity is important at large scales, where quantum effects are negligible. Quantum effects are important at small scales, where gravity is the weakest of the four forces and can usually be ignored. The regimes where both are simultaneously essential are rare and extreme, but they exist. The center of a black hole is one. The first moments after the Big Bang are another. The Big Rip singularity is a third. As the Hubble parameter climbs toward its infinite value in the final moments of a phantom universe, the energy density of dark energy is climbing with it. At some point in the approach to the singularity, not at the singularity itself but before it, the energy density of empty space exceeds the Planck energy density, which is the scale at which quantum gravitational effects become impossible to ignore. This is not a number derived from observation. It is a number derived from the fundamental constants of nature, the speed of light, Planck's constant, and the gravitational constant combined into a unit of energy per volume that defines whether known frameworks stop being reliable. The Planck length is approximately 1.6 times 10 to the minus 35 meters. The Planck time, the time it takes light to travel one Planck length, is approximately 5.4 times 10 to the minus 44 seconds. At these scales, the smooth, continuous spacetime of general relativity is expected to break down. Whether spacetime is actually discrete at the Planck scale, whether it foams or granulates or behaves in some other way that no current theory fully captures, is genuinely unknown. String theory proposes one set of structures at that scale. Loop quantum gravity proposes another. Several other approaches exist, each mathematically self-consistent, none confirmed by experiment. What they agree on is that something different is happening at the Planck scale, that the smooth manifold of general relativity is an approximation that works at larger scales but stops working there. In the approach to the Big Rip, the characteristic length scale of the universe, the scale at which the physics of expansion is operating, shrinks. As h increases, the Hubble length, roughly c over h, the distance at which recession velocity equals the speed of light, decreases. It passes through galaxy scales, stellar scales, atomic scales, nuclear scales, all on the way down. At some point before the mathematical singularity, it crosses the Planck length. At that crossing, general relativity, the framework that produced the Big Rip prediction in the first place, is operating outside its own domain of validity. This is the corridor, and the thing at the end of it is not a door exactly. The notebook on the floor with its spine bent the wrong way, left there from earlier 2 nights ago, some half-formed calculation that didn't resolve, has nothing to do with any of this. But it is here, in the room where this is being written, and that feels like the right kind of detail for this particular chapter. Something incomplete, something that didn't quite close. What happens at Planck, soils in the context of Big Rip, is not described by any current theory with confidence. This is not evasion, it is the actual state of the physics. The Caldwell et al. Paper from 2003 that introduced the Big Rip worked within general relativity, as it had to, and noted explicitly that near the singularity the classical treatment breaks down. Subsequent work has explored what various quantum gravity approaches might predict for the behavior of phantom cosmologies near their singularities. Some models suggest the singularity could be resolved, that quantum effects might modify the phantom energy's behavior at Planck scales in ways that prevent the divergence, turning the Big Rip into something softer, a rapid expansion that slows or bounces rather than diverging to infinity. Some models suggest the singularity persists in a modified form. Some models do not make a clear prediction at all. This is the genuine epistemic situation, not a gap waiting to be filled by a known method, but a boundary where the known methods stop producing reliable output. The question of information is related, and it is worth pausing at briefly without trying to resolve it. In quantum mechanics, information is conserved. This is not a casual claim, it is a fundamental principle closely tied to the unitarity of quantum mechanical evolution. The complete information about the quantum state of a system at one time determines the complete information about its state at any other time. Information does not disappear. It may become inaccessible, scrambled, distributed across enormous numbers of degrees of freedom, but it is not destroyed. In the approach to the Big Rip, as the scale factor diverges and all structures dissolve, the question arises of what happens to the information encoded in those structures, the atoms that made up a galaxy, the quantum states of every particle that was ever in every star, If the singularity is a true singularity of space-time, a boundary where the manifold ends, then the question of where the information goes is as unresolved as the question of what exists at the singularity. Whether information survives a Big Rip singularity is not known. Current physics does not have the tools to answer it. What quantum gravity does with information at a space-time singularity is, alongside the black hole information paradox, one of the deepest open questions in theoretical physics. The Big Rip version of the question has received less attention than the black hole version, partly because black holes are confirmed to exist and phantom energy is not. But the structure of the question is similar, and the answer, whatever eventually is, would require the same framework that doesn't yet exist. The corridor this chapter described at the beginning does end. The approach is long and traversed step by step, galaxy clusters, then galaxies, then stars, then atoms, then nuclei, then the Planck boundary. And at each step, the physics is still doing something, still producing equations with solutions, still generating predictions about what would happen next. All the way down to the Planck threshold, the mathematics is operational. At the Planck threshold, it stops being operational in the sense that matters. Not because the equations vanish, they are still there, you can still write them down, but because the solutions they produce are no longer descriptions of anything the physical world can enact. The manifold of space-time that the equations describe is the same manifold that would have to exist for the equations to mean something. And at Planck scales that manifold is not reliable. It may not exist in the form the equations assume. The physics runs out not with a declaration, not with a boundary marked on any map. It runs out the way a path runs out in terrain that was never meant to be a path. Gradually, the markers becoming less, the ground less navigable, until you are somewhere the path did not anticipate and the path does not help. The door is not there. The corridor ends in wall, or in something that is neither wall nor opening, or in a change of conditions so complete that the word corridor no longer applies to what you're standing in. This is where the describable ends, not here, in this chapter, a little further, but close. The floor is cold in the morning. That specific, unremarkable fact, bare feet onto tiles that have been sitting in a house that has been sitting in a city that has been sitting on a planet, is possible because of a chain of conditions that extends in every direction through space and time, each link of which is, at this particular moment in the universe's history, intact. The floor is solid because the atoms that make it up are bound together by electromagnetic forces that are, at the temperature and pressure conditions of an ordinary room, completely stable. The feet are warm because metabolic processes are converting stored chemical energy into heat, processes that depend on the same atomic chemistry, the same nuclear physics, the same cosmological conditions that allow stars to burn and planets to form and matter to be matter. None of this is remarkable in the sense of being unusual right now. It is just what the universe is doing at this stage of its existence, holding together, processing energy through structures at every scale from subcellular to cosmic, running the physics that it had been running since the first atoms formed 380,000 years after the Big Bang. With modifications, stars condensed, heavier elements were forged, galaxies assembled, planets cooled, chemistry happened, but the underlying coherence intact throughout. The universe is still here. We are still here inside it. That is the only fact this chapter is about. What coherent means in the context of this moment is specific. It means that the forces holding structures together are stronger at their respective scales than the forces pulling them apart. Gravity holds galaxy clusters in loose gravitational conversation. Gravity holds galaxies together as rotating structures with persistent form. Gravity holds stars as contained fusion reactors. Gravity holds planets in orbits. The electromagnetic force holds atoms together as atoms, holds molecules together as molecules, holds the matter in a floor or a hand or a wall together as a solid thing rather than a dispersal. The strong nuclear force holds the protons and neutrons inside every nucleus together, against the electromagnetic repulsion of protons pushing against each other at nuclear distances. All of these things are true right now, simultaneously. At every scale from the subatomic to the cosmological, the binding forces are winning. This will not always be true. Whether it stops being true because of the Big Rip, because phantom energy strengthens until the Hubble parameter overtakes each of those bindings in sequence, or because of the slower thermodynamic exhaustion of a big freeze, or because of some other future the current data hasn't resolved. The present coherence is not permanent. It is a condition, a stage. The universe is in a phase where matter holds together and light travels between things that still exist, and the distances between observers and observed still have physical meaning. The light reaching a telescope tonight left its source some time ago. Depending on the source, that time ranges from minutes, the sun, 8 minutes, to billions of years. Distant quasars whose light has been travelling since the universe was a fraction of its current age. All of that light is arriving. The sources still exist, or existed, and the path from there to here was traversable, and the detectors built to receive the light are themselves coherent enough to detect it and record it, and allow inference about what produced it. This is, in the context of what the last several chapters described, a specific and temporary condition. In the long quiet before a big rip, billions of years into the phantom era, before any structure has yet failed, this would no longer be true for most sources. The light from distant galaxies would have stopped arriving. The shrinking Hubble horizon would have removed them from the observable universe one by one, and the sky would be carrying less information than it carries now, fewer messages from fewer sources, the cosmos communicating with itself across shorter and shorter distances. Right now the distances still have meaning. The light still arrives. The sky is still full. The Hubble tension, which ran through the earlier part of this script like a thread that wouldn't pull free, is still unresolved. The DESI data is still being collected. The question of whether dark energy is a cosmological constant or something that moves, whether the equation of state sits at -1 or has drifted below it, whether the scale factor is heading for a plateau or a singularity, none of these are settled. The measurements will continue to improve, the constraints will tighten. At some point in the next decade or two, the data will likely be precise enough to distinguish between a constant dark energy and a dynamic one with statistical confidence. Whether that answer changes anything about the present is a separate question. The present is what it is regardless of what the future holds, and what it is, specifically, is a universe in which physics still works at every scale, in which matter coheres, in which the laws that allow observation and inference and measurement are still operational. That is not a small thing, even if it is not a permanent one. It is just a thing. Allison has been part of this space since the beginning, and Matthew M. and Brian Winter are co-creators in the truest sense. Without them, these scripts wouldn't exist in the form they do. Every Patreon member who has supported the Sleepy Physicist is part of why this particular corner of the internet is still running, still making things. If you have found something in these chapters worth returning to, the link to the Patreon is in the description. The universe is approximately 13.8 billion years old. The first stars formed around 100 million years after the Big Bang. The Sun formed about 4.6 billion years ago. complex chemistry on this planet has been producing increasingly elaborate structures for billions of years, and the particular kind of structure that asks questions about the universe, that builds telescopes and runs spectroscopic surveys and argues about the value of the Hubble constant to 3 decimal places, has existed for a vanishingly small fraction of that time. This is not a setup for a statement about significance. It is just context. The universe has been running for a long time before any part of it became capable of noticing the expansion, and it will run for a long time after. In some form, through some future, the current physics can partially describe and partially cannot, whether or not anything is there to notice. What is true right now is that something is noticing. The structures that allow noticing are intact. The instruments work. The photons arrive. The atoms in the detectors respond to the photons in ways governed by well-understood physics. And the well-understood physics produces data. And the data is argued about by people who care about the answer. And the caring produces more careful measurements. And the measurements will eventually tell us something true about the nature of dark energy. That chain, from photon to detector to data to argument to understanding, is the coherent moment. It requires matter that holds together, forces that work, distances that are traversable, time that is still running in a forward direction through a space-time manifold that has not yet encountered its own limits. All of those conditions are met, right now, in this particular era of this particular universe. What comes after? Whether the universe ends cold or in structural catastrophe, whether the singularity is real or resolved by a physics that doesn't yet exist, whether information survives or the question stops making sense before it can be answered, is genuinely unknown in the ways that matter. The data will improve, the theories will sharpen or dissolve, the picture will change, but the picture exists right now. The universe is still here to be pictured. Matter is still holding together long enough to wonder about what holds matter together. Light is still arriving from distances large enough to map the expansion history of the cosmos. The Hubble tension is still open and producing data and argument and new measurements that will eventually, probably, tell us something real. There is nothing in that situation that demands a conclusion. It is just an observation about where things stand. The scale factor is climbing. The Hubble tension sits unresolved at 5 sigma. Deci is still collecting galaxies. The Planck boundary sits where it has always sat, at the edge of what the known frameworks can describe, waiting for a theory that doesn't exist yet. And the floor is cold in the morning, and the atoms of it hold together, and the light is still arriving. The universe may or may not tear itself apart in the far future, but either way, I feel like I need a nap after all of that. See you in the next one.